Last time we talked about writing Lewis structures, and we are going to continue with something called the formal charge. Now, the formal charge is the charge assigned to an atom and a molecule, assuming that electrons in a chemical bond are shared equally between atoms, regardless of their relative electronegativity. So the formal charge, you assign formal charges to the molecule or to the atoms right after you finish everything about the Lewis structure. Like once you finish drawing Lewis structure, the last step will be assigning the formal charge. Now I'm going to teach you. This is how the book is assigning the formal charge. The formal charge in an atom is equal to the valence electrons minus the total number of non-bonding electrons minus half the total numbers of bonding electrons. I honestly do not use this method. I'm using an easier one. I'm going to teach you that in a few seconds. But the importance of formal charge is that for neutron molecules, a Lewis structure in which there are no formal charges is preferable in one in which formal charges are assigned. So that's the first rule for formal charges. We are trying to minimize formal charges. That's the whole thing. And a Lewis structure with large formal charges are less reasonable than those with the small formal charges. So rule number 1 says try to minimize the formal charges, try to eliminate them. Rule number 2 says if you are having formal charges, try to minimize them. And rule number 3 is that among Lewis structures having similar distributions of formal charges, our most probable structure is one in which negative formal charges are placed in more electronegative atoms. So these are the 3 scenarios that you have for formal charges. The first rule says 0 formal charges is the best, okay? No formal charges, this is the best situation. Rule number 2 says if you have formal charges, try to minimize them. So a +1 is better than +2, and -3 is better than -2, and so on. And the third rule says if you have no way but to have formal charges, at least try to put the negative one on an electronegative element, okay, or the most electronegative element. And let's start with an example that we did last time, which is NF3, and I'm going to teach you how to do the formal charges. So we are repeating this example from scratch. So NF3 is the one we solved last time. The first step in drawing Lewis structure and determining the formal charges is first we count the valence electrons. So valence electrons for this element is equal 5 because nitrogen is in group 5, plus 7 times 3 because fluorine is in group 7. And that will give you 7 times 3, 21 plus 26 electrons. And therefore your Lewis structure should have 26 electrons. The second step in drawing a Lewis structure is you make at least one bond for each element. Okay, so this looks promising, but the problem now we don't have 26 electrons here. We have only 2 and 4 and 6. Each bond is 2 electrons. Remember this. Each bond equals 2 electrons, and this is called bonding pairs. Okay, so now we have to draw the left. So we get 2 here, 2 there. Okay, let's complete that. So how much we have here? 8 times 3 is 24. Now we have 2 electrons left. We put them in on the nitrogen. So this is the Lewis structure of NF3. Of course, this is not the actual structure, but this is a good structure for nitrogen trifluoride. Now, usually for speed and convenience, what people do is they draw the non-bonding pairs, the lone pairs, as dashes. So here we can say, and instead of writing these small circles and just to speed up time, we can do this. And so this is 2 electrons here, 2 electrons here, 2 electrons here. So each dash here is 2 electrons, okay? That's just another way to draw Lewis structures. It's faster. This is what people do in Canada. Anyway, now let's count the octet rule, okay? So octet rule here is in red for each element. Now this fluorine to the right has how many electrons? It has 8 electrons, as you see here. So 2, 4, 6, 8. This is 8 electrons around fluorine, and this is 8 electrons around fluorine, and this is 8 electrons. For the nitrogen in the middle, we have 2, 4, 6, 8. Okay, so if you count them around nitrogen, you will have 8 electrons as well. The dash above the nitrogen, this means 2 dots, okay, or 2 electrons. So this is a very good Lewis structure because it achieves the octet rule for everyone. And remember, we have 4 elements that we cannot play with anyway. C, N, O, F. These elements, they have 0 tolerance with the octet rule. The octet rule must be satisfied for them. Okay, so let's now move on to teach you the story of formal charges. So I'm going to use the same example to teach you how to do a formal charge for this element, for this compound, for this molecule. Now, remember, this is our molecule here. And these are all the electrons around it. Okay. Now, I am going to use this color, the blue color, in order to count the formal charge for each element in this compound. Now, my way of doing the formal charge is that it's equal actually the valence electrons minus the actual electrons. That's simply like that, okay? So let's do that for one of these elements. I'm going to do it over and over so you can learn it, okay? This is the rule for formal charges. That's just a simple rule here. So to count the formal charges, I want you to pay attention how to do it, okay? So for this fluorine to the right, fluorine has 7 electrons around it. This is, okay? So fluorine has 7 electrons. That's a valence electrons. That's a fixed number. It doesn't change, okay? And then minus. Now let's count how many actual electrons are around fluorine right now. Now we have 2, and then 4, and 6. And this bond here, I'm going to take half of it. And this is different than counting for the octet rule. So I'm going to take half of that bond. I'm going to count only 1 electron for fluorine, so that's 7. And this is equal 0. So fluorine has now 0 formal charge on this fluorine. This is also 0, and this is also 0. Now let's take for the N. The valence electron for nitrogen is 5, and then minus. Now how many electrons are around nitrogen for now? This is 2 electrons. We count all of them because this is a lone pair, and this is only 4 electrons. I'm going to take this half bond, okay? So that's 1 electron. And this is also half, and this is half. So I'm going to count 1, 2, 3, 4, 5. Did you see how I counted the formal charge? Again, I'm going to count for nitrogen. So I'm going to count 2, 3, 4, 5. Okay? So this is 5, and this is equal to 0. So NF3 is easy. It has 0 formal charges for every element. Okay? I'm going to try this for another. We're going to do this again and again today. So you will learn how to do it. Now let's start actually with a real example that involves some formal charges. We're going to today to draw the Lewis structure of ozone, O3, and see how does it look like, does it have any formal charges, and so on. There's so much to learn about ozone, but let's start with writing the Lewis structure. For ozone, the Lewis, first of all, the number of total electrons, we have 3 times 6, because oxygen is in the 6th group and it has 6 valence electrons, so we have 18. And we start by writing first a single bond for each oxygen. Now, if you want to distribute the 18 electrons, you can put for this guy, because you want to achieve the octet rule for each one, right? So this one So how much is that? 8 and 8, 16. You have 2 more. There is no way but to put them here. Okay. So this is one of the lowest structures of ozone. Okay. Actually, it looks like this, but I'm gonna, as I told you, I am using dashes instead of circles. But anyway, now let's see what happens to how does the octet rule for this ozone molecule first looks like. Now this guy is 8. I hope that now you know how to count for the octet rule, and this guy is 6. So this is not acceptable structure for ozone. This is not acceptable structure because remember CNOF cannot break the octet rule, and therefore oxygen is one of them. That's totally unacceptable as a lowest structure. So one of the ways to solve this is you bring this lone pair and you make a bond. So this will lead you to this structure. So we made a double bond here. So this will leave you with 2 lone pairs here, and this guy will be untouched. Now let's see how this works. This now has 8 electrons around it, 2, 4, 6, 8. This one 2, 4. I'm counting for the octet rule. I'm counting for the octet rule, so I'm counting this bond as complete. Okay. So 2, 4, 6, 8. You see that? I'm not doing. Sorry, I'm not doing formal charges here. I'm doing octet rule. So 8 for this guy, 8 for the guy in the middle, and this is 8. So this is very good for lowest structure for ozone. You might also do it like that. And instead of the double bond be in the right, we can in the left, we can put it on the right, and this will be looking like this. Okay. These are two, of course, these are called resonance structures, okay, because they are mirror images of each other. They are the same, but the double bond one time is in the left, one time is in the right. This is called resonance structures. Right. Now let's forget about this guy for a second, and let's focus on the formal charges. Ozone has formal charges. I'm gonna count them for you in different color. I'm gonna put here this color here in the blue color, okay? So the formal charge for this oxygen is equal. Oxygen is 6, so valence electrons minus actual. So oxygen is a group 6, so it has 6 valence electrons, and this is a number that is fixed, it doesn't change. Minus how many electrons around oxygen right now? We have, I'm gonna do this for you. 1, 2, 3, 4, 5, 6, 7. Did you see how I counted the bond as half bond? And this is how you do it, okay? So we have 7 electrons here around oxygen. So this is minus 1. And this is, so oxygen, in this case, this is equal minus 1. So this oxygen has minus 1 formal charge on it. This oxygen has 0 because it's 6 minus. Where does the first 6 come from? The first 6 is the valence electron for oxygen. This doesn't change. It's a group 6, so 6. Minus, if you count this 1, 2, 3, 4, 5, 6. So this is 0. And this one, the one in the middle, 6 minus, you have 1, 2, 3, 4, 5. Oh, wow. Okay, so this is actually going to be 6 minus 5, which is equal plus 1. So ozone then has this lowest structure. It actually looks like this, where you have a negative 1 here and a plus 1 here. And as you see here, the total number, the total formal charges in a compound should equal to the total charge. Of the molecule or the ion we are dealing with. Ozone is a neutral, so it has no charge at the beginning anyway. When we started with ozone, O3, it's not O3 minus or O3 plus, it's just O3, and therefore it's ozone layer as we know in the atmosphere, and therefore the sum of formal charges, so plus 1 and minus 1 is 0, and therefore the charge is 0. Okay, does anybody have questions or anything? I'm just gonna do something here on Blackboard for you guys. Does anybody have questions so far? Okay, so okay. Now let's do another compound, which is easy one, and see OF2. Okay, OF2 is you have 6 plus 7 times 2. 14 and 6 is 20, is it? Yeah, 7 plus times 2 is 14 plus 6, 20 electrons. So I'm going to do that. So OFF, that's easy. Maybe try something. Oh, sorry. Yeah, OF2. So how much is that? 8 plus 8 is 16, and you need 20 electrons. So there is no way but to add the electrons here. So this is OF, the lowest structure for I'm gonna do it in two ways, okay? One with a circle, so you start getting to know. Now let's see how we are doing with octet rule and formal charges for this molecule, and see if we need double bonds or triple bonds. So I'm gonna do the octet rule in red. So this one 2, 4, 6, 8. That's 8, and this is 8, 8. Gonna do the formal charges in the blue. I'm gonna do this. So this guy is in group 7 minus how many electrons right now around it? 2, 4, 6, 7. You see, I'm counting this bond as half, if you are following me. So 7 times 7 is 0. This guy will be 0, and this guy will be 0. For the oxygen in the middle, oxygen is in group 6. So 6 minus how many electrons around it right now? We have 2, 4, 5, 6. I'm counting the bond as half for the formal charge. So 6 minus 6 is 0. Oh, wow, this is a very nice. So OF2 is actually a molecule that achieves the octet rule. So we have, we're going to pass it for the octet rule and also for formal charge. It's actually doing both. It has both OKs for the octet rule and the formal charges. So if you go to Blackboard, and I want you to do that, everyone, please, right now. So, and this is the class activity for today. You open the course, which is Chemistry 101. And if you go to assignments, you go all the way down, you click on class assignments for Ismail. That's the last page, that's the last one at the bottom of the page. So go to Blackboard, please, everyone, and go to assignments and pull the page down all the way to class assignments. If you click on that folder, you will see three assignments. We have done the first two actually. Now we're going to click on the third assignment. I'm going to do that for you. Once you click on the third assignment, that will open this instruction. Begin. And here in the first question, it says the formal charge in oxygen in F2 is. Write the answer as a digit. So this is OF2. What is the formal charge on oxygen? It is 0. So write this number as a digit. So you just put 0 on the square here. Okay, OF2, 0. Then let's move on to more complicated examples. And we're going to do now sulfur dioxide, SO2. And we're not only going to work on formal charges and octet rule, but we're also going to learn more about the resonance and the phenomena of resonance. So SO2, let's start right from the beginning. So SO2, we need first to count the number of electrons. So we have both oxygens and sulfur are in group 6. So we have 6 plus 6 times 2. We have 18 electrons. Now, which one is the middle bond or the middle element? Of course, the one with the lowest electronegativity, which is sulfur, and therefore we put sulfur, oxygen, oxygen. That's a good start. Single bond, single bond. Now these are only 4 electrons. We need to put 18 electrons. So we need to complete the rule for everyone, right? So this is like that. How much is that? 18 plus 18 is 16, and therefore we have 2 electrons in the middle. This is, let's see how we are doing here. First of all, in terms of octet rule, this guy has 8, and this guy has 8. Okay? And this one has 6. Wow, this is a questionable lowest structure, because you're not achieving the octet rule for everyone, and you have a chance to do that. Okay, you have a chance. An easy way to do that is just pull these electrons here, and therefore this will lead you to a better lowest structure that looks like that. Yeah, but the next question is about SO3. So you watch my presentation, and then we can answer the question together. Is that okay? Okay, guys? So just answer the first question, which is OF2, the charge is 0. So now, this is, let's see how we are doing with the octet rule first. Here we have 8, and we have 8, and the sulfur has 8, 2, 4, 6, 8, so that's good. This is a good Lewis structure, but this one has another resonance structure, where the double bond is actually on the left. I'm not rotating the molecule, I'm just moving these electrons that make a double bond to the other side. Now this is another Lewis structure for SO2. And this one also has 8. And guess what? These structures are different in. They are different in their formal charges. Because when you count a formal charge, for those oxygen to the right here, and we did this before, this is -1. Because this is a 6 minus 7. If you count the electrons around oxygen, they're going to be 2, 4, 6, 7. Because for formal charges, you count this bond as half. The lone pairs here, they belong to oxygens. 2, 4, 6, and then 7. So 6 minus 7 is -1. You will find this to be 0. And for the sulfur in the middle, sulfur is in group 6. So minus, you have 2, 3, 4, 5. Did you see how I'm counting this? I'm going to do this again for you. So for the sulfur, we have 2 electrons, because these 2 electrons, they belong to sulfur. That's the lone pair. 2, 3, 4, 5. I'm taking half the bond. Half the bonding pair. So 6 minus 5 is equal +1. Well, even if you don't know it's +1, it should be +1, because SO2 is a neutral, and -1 and +1 is 0, and therefore the formal charges is 0. This will be the other way. This will be -1 here, +1 here, and 0 here. So you see how these two Lewis structures, they are different. In both cases, you have sulfur to be +1, and the oxygen, the two oxygens, they alternate the formal charge. One is taken 0 and one is taken -1 at a time. These are two acceptable Lewis structures. They are equal Lewis structures, and this is called resonance. Not all elements, not all compounds, they exhibit resonance. Some of them they do, and SO2 is one of them. SO2, it can exhibit resonance, and the definition of resonance is that we have two equivalent Lewis structures where they are different only in the distribution of the electrons. Okay, here there is nothing. The only difference between these two is that these two electrons here, this bond is sometimes one time is here, one time is there, and these two electrons here, I'm going to make them in a box. Sometimes they are here, sometimes they are there. And you know, lowest structures, it's very weak model anyway. And the actual, and nobody will tell you exactly where are these two electrons except quantum mechanics. And the quantum mechanics, of course, says that electrons are everywhere. And therefore, experimentally, we found that the SO2 is actually it's not like this bond is single, is double bond, and this one is single, and at 50% at some time. The matter of the fact actually is that because these two Lewis structures are equal, the bond length here between the SO is actually 1.5. It's like this is a bond, is like this is 1.5 bond. Okay, it's not actually this is a double bond and this is a single bond, because these two electrons, the ones in the box, they are distributed among the whole system, and they make you, because they're sitting 50% of the time here, 50% of the time there, and therefore they make you kind of have a 1.5 bond. So this is called a hybrid structure. It's like you make a hybrid out of two things, okay? Just like the hybrid car. Anyhow, we'll do some more and I will teach you more about this resonance. But for now, SO2, it can make resonance, so therefore we can go on, move on to the second question. And says, the question 2 says, sulfur dioxide, SO2, can demonstrate different resonance structures. True or false? What do you think? Answer window? True, yeah, of course, it's true. So you put, everybody put true, please. Okay, moving on to the next example. And I have here NO2 minus. Let's see NO2 minus, okay? NO2 minus is the nitrite ion, not nitrate. You can do the nitrite as well. This is called nitrite ion, like KNO2 or HNO2. And we'll do this. This is the first time we'll do a molecule with a negative charge or an ion. Let's count the electrons first. The electrons is the so total number of electrons is equal. You have nitrogen is a group 5, so this is 5. Oxygen is a group 6, and you have +1 for the extra ion, extra electron. NO2 minus means you have an extra electron sitting in the molecule. So 6 times 2 is 12, 18. You have 18 electrons in this molecule. So we start by a single bond for each NO2, okay? Now you have to put 18 electrons. So we're going to do our dashes for the oxygen just to fulfill the octet for oxygen. And this is just similar to actually, this is very similar to the SO2, because nitrogen is not fulfilling the octet rule here. So this one is unacceptable Lewis structure, and therefore you will have this structure for NO2, which does make sense, okay? And it's the same story here. You have -1 there, 0. But for in this case, nitrogen does not have a +1 formal charge like SO2, because nitrogen is a group 5, and when you do a formal charge calculations for it, it's going to be 5 minus how many electrons around it? We have 2, 3, 4, 5. So 5 minus 5 is 0, and therefore nitrogen NO2 minus has a 0 formal charge. So in this case, you have two structures for NO2 as well. NO2 minus can make resonance, where the double bond is one time is in the left, one time is in the right. Okay. In this case, you have a -1 here and a 0, 0 here. Or it could be -1 to the right and 0, 0 to the left. Okay. So these are two resonance structures for NO2 minus, where actually the actual bond is not neither single bond or double bond. The hybrid structure will be something like this. Okay, where this actually is not A single bond, neither double bond. This is kind of 1.5 bond. It's in between these two bonds. So NO2 can make two resonance structures. Now, one might say, teacher, why you are only limiting yourself to one double bond? I'm gonna make NO2 like that. Like I'm gonna make, because here you said this is not accept the lowest structure, and you brought this two electrons to make a double bond, and one student jumps up and says, okay, I'm gonna make another double bond here. Okay, well, in lowest structure you can do whatever you like. Everything is possible, but you have to think about your answer. Now, remember we have 18 electrons in this compound, so now we have 2, 4, 6, 8. So I'm gonna complete the electrons for this. 8 and 8. Okay, so this might be it. Now look at this structure. What do we have here? We have 8 as in terms of octet rule. We have 8 octet rule. Now what about this nitrogen in the middle? We have 2, 4, 6, 8, 10. This structure, it violates the octet rule because nitrogen cannot stand 10 electrons, and therefore this one is not acceptable lowest structure. So you can try to draw a lowest structure, that's fine, you can try whatever you like, but you have to judge your structure based on the octet rule and the formal charges. And the octet rule is important for these elements, CNOF. And also this one actually has what? Like this one is 0, this one is 0, this is -1. Yeah, in terms of formal charges, that's fine. You have the -1 in the middle on nitrogen, and that one in the top is in oxygen. But this one has a big problem with the octet rule, okay? So the octet rule here failed, formal charges passed, but we prefer the octet rule for the CNOF. CNOF, we cannot play with the octet rule, and therefore this is not acceptable structure. So going back to the example, just like this is an extension of that. NO2 does two resonance structures. One is the double bond to the left, one double bond to the right, and the hybrid structure is something in between. And I just teach you how to do it for octet rule and formal charges. And we're not done yet. We're going to do a lot of examples until you guys practice this really good. Anybody wants to answer question 3, please? Out loud in the microphone as part of your participation. Anyone wants to? Yeah. No, you need to read the question. Can you read the question loud, please?
The sum of total charges in the lowest structure should equal to the total charge of the molecules or atoms.
Yeah, is this true?
Yeah, I think.
True. An example of this is NO2 minus. Look at the sum of the formal charges. 0 plus 0 plus and -1 is -1. And we are working with NO2 minus at the beginning anyway. We are working with NO2 minus, okay? So the sum of total charges in the molecule should equal to the total charge on the ion or molecule. So guys, just to be in the same page here, you have till 9 o'clock to finish this exercise, this class assignment. We are doing this class assignment for the people who are joining us. Please go to Blackboard, and we are doing a class assignment number 3. So we are in question 3 now, and you have till 9 o'clock to finish it. Okay. Let's move on to another example, which might be kind of controversial, but we will do it because we are enjoying our teaching here. We are as NO2, okay? That's not NO2 minus, that's NO2 gas. Nitrogen dioxide is called. Okay? Nitrogen dioxide is a gas that exists in the atmosphere. Okay, this is not a minus. This is not an ion. This is just a covalent compound that exists by itself. Counting the electron for this guy will be 5 plus 6 times 2 for the oxygens. So you have 17 electrons, and this is the first time we are seeing odd numbers of electrons. When you want to do that, you might try to do it first by drawing a single bonds for the oxygen, and you fill the oxygens here. This is the first step. Of course, that's not good. Oh, sorry. Now you have to add 17 electrons, so you fill for the oxygens, that's 8 and 8, 16. And now you have only 1 electron for the nitrogen in the middle. Okay, well, you have no other electrons, so you have to stick with what you have. Of course, this one violates the octet rule badly, because under this situation, this guy is 8, and this guy has 8, but this guy has 2, 4, 2, 4, 5. That's very bad Lewis structure, very bad Lewis structure. Okay. And by the way, I forget to do something in the previous slide, is that when we do it for the NO2, because it is okay, sorry guys, I made a mistake. It's a minor mistake. Whenever you do something for an ion, you must include it in brackets and you add the charge. So this one is actually -1 here. Okay, everything here. You don't have to do this for neutral compounds, but whenever you do a Lewis structure for an ion, you make it -1. Okay, let's go back to the NO2. So now you have an odd electron sitting on nitrogen in the middle, and this one has a big problem. It violates the octet rule badly, because you have only 5 electrons for nitrogen. That's not unacceptable. So the best thing is to bring maybe a double bond here that will solve part of the problem. So you'll have this structure for NO2. Now we took 2 electrons to make a double bond, so that will leave you with 4 here. This one is untouched, so I'm going to keep it like that. And now this guy has 1 electron. Honestly, you cannot do better than this. You can try to make another double bond, but let's see how we are doing here. We have 8 here, we have 8 there, 2, 4, 6, we have 7 here. In terms of formal charges, this is a -1, we did before. This is 0. What about the nitrogen in the middle? We have 5 minus 1, 2, 3, 4, that's a +1. Okay? This structure is actually the structure of NO2. It violates the octet rule, okay? And this is called the free radical. Free radical means something that has an odd electron in it. So NO2 is actually this one. There is no doubt that NO2 is this molecule here. We have, even if you don't want to write the electrons on the oxygens, but this is called a free radical. It has an odd electron. It violates the octet rule because nitrogen has 7 electrons around it, 2, 4, 6, 7. But we cannot do anything. We have nothing to do about it. We cannot solve its problem. So it exists in nature, and that's what. And the people, when write this down, they call it NO2. Okay, they write a dot to indicate that this is a free radical. And free radicals are very reactive. Like once an NO2 sees another NO2 molecule, they can actually make a molecule called N2O4, which is dinitrogen octoxide, dinitrogen. This is a covalent compound. Tetroxide. Remember, tetraoxide, so we drop the A. And this, of course, all gases, and they exist. So, but that doesn't mean that this reaction is very slow, and it goes in equilibrium. So, but NO2 does exist in nature. Okay, it exists in the atmosphere, and it's available, and it's actually the one that causing the colors of the sky to be kind of reddish at the evening. Type. So now I teach you here 2 things about NO2. That NO2 is one of the compounds that they violate the octet rule. Okay, and it does actually resonance structures as well. So you have 2 equivalent Lewis structures because you have this one, but you have the other one with the double bond to the right. And I taught you about the octet rule, the formal charges, and the octet rule as well. Okay, so far so good. We did NO2 minus and NO2. We did also SO2. And let's go over other stuff from the. So you can do this at your house, this question, carbonate. So this is the example of the O3 in the slides. I've done it for you as well. It's more clear. This is the way you represent Lewis hybrid resonance and the actual structure. CO3, we're gonna do it next time. Carbonates actually also, or you can do it by yourself if you like at home. You will discover that carbonate ion does also resonance. It's benzene ring. It's a famous example of resonance where the double bonds, they rotate or they change the places, and the actual structure is something as a hybrid structure. We didn't do this in 2O, we can do it later. But I need to talk about this, exceptions to the octet rule, exceptions, okay? Exceptions is that NO2 is one example of the exceptions. And where you have incomplete octet. And some of the atoms that do exceptions is that actually the beryllium and boron are elements that they cannot achieve the octet rule. Just like hydrogen has only one electron, and the maximum electrons can take in a compound is 2. So it violates so hydrogen itself violates the octet rule. But look at this example, BeH2, beryllium hydride. Beryllium is in group 2, so it has 2 electrons, and therefore you have 2 plus 2 times 1 is 4. So this molecule, the whole electrons in it is only 4 electrons. So you want to do a single bond, you want to put B in the middle, single bond for hydrogen, single bond for hydrogen, you're going to get into this. So how many electrons? 4. You don't have anything extra. Nothing extra here. There are no lone pairs around beryllium, okay? 0 lone pairs. Because that's 4 electrons that you're having, they are already busy in making bonds. If you look at the hydrogen has 2 electrons around it, so it violates the octet rule. Beryllium has 4 electrons around it, and it violates the octet rule, but there is nothing to do. What, are you going to bring electrons from your house? That's it. So therefore, this is called incomplete octet, and beryllium hydride is a molecule that violates the octet rule, but that's okay, because there is nothing to do about it. BF3 as well. So beryllium and boron are the same thing. So if you do the math for boron is in group 3. Okay, a third period 3 and plus the 3 fluorines, you will have 204 electrons. Fluorine cannot break the octet rule, so this is the Lewis structure for boron trifluoride. If you assign, if you count the electrons, you will find it be 24, because 8 times 3 is 24. In terms of the octet rule, all the fluorines are good. Each fluorine has 8 electrons around it. Okay, and for boron, it has only 6 electrons around it, and this is really, really bad. But this structure violates the octet rule, but it does exist. It's the only structure for boron trifluoride. If I ask you what is the distribution of formal charges in BF3, that's a good one. So BF3 looks like this. We have 2, 4, 6 here, 2, 4, 6 there, 2, 4, 6 there. And if you count this, 8 times 3 is 24. These are the total numbers of electrons of BF3. If you want to count the formal charges, and let's practice this again, fluorine is in group 7, and then minus 2, 4, 6, 7. So 7 minus 7 is 0. Because the way I count it is that this is 2, 4, 6, and then 7, okay? So 7 times 7 is 0. So this is 0, 0, 0. Boron is in group 3. So 3 minus 1, 2, 3. Oh wow, 0. So boron also has a 0 formal charge. In terms of octet rule, this guy has 8, this guy has 8, this guy has 8, but boron has how many? 2, 4, 6, okay? So BF3, it passes the formal charges test, but it fails the octet rule test, and therefore we say this structure, it violates the octet rule, but unfortunately we cannot do anything about it. So this is the actual acceptable structure for BF3. NO2, I told you about it, and we did it before. This is NO at the beginning. We have not done NO, but when you do NO, you will also find it to be a radical, where you have an odd electron sitting in nitrogen. So both NO and NO2 are called free radicals, and they are some examples of compounds that violate the octet rule. And as I told you, NO2 dimerizes, okay? So it acts by itself to form this NO2O4, which is a more stable compound. Doesn't mean that NO2 does not exist. It does exist. But these are also examples of compounds that they violate the octet rule.